Oh, I can see. I can see Anthony on the line. So this morning we'll start discussing porosity, formation density log, which is part of porosity log.
Good day, sir.
How are you?
I'm fine, sir.
I'm sorry for all the inconveniences. It's not actually intentional. So somehow it comes away. I lost one of my in-law in Akure here in this recent time, and has really been some up and down. So please pardon me. How many of you are online now? You are the only one, right?
Janet has come.
Okay. Now, like in the last classes, we discussed lithology log, we've discussed resistivity log, and now we are discussing porosity log. And we've made transit that is called interval transit time of the borehole, which we but today we are going to formation density log called gamma log. Gamma log. This is a which is essentially a gamma log. It is artificially introduced to the formation. The radioactivity substance is artificially introduced to the formation, unlike the gamma ray log, where you have the log sound recording gamma radiation from the radioactive element present in the formation. But in case of formation density log, the radioactivity itself is artificially introduced. Hello, are you listening? Hello?
Hello, sir. Network.
Why are people so selfish? They only concern about themselves, Joe. Oh, okay. Now. Hello?
Hello, sir.
Yes, sir.
Yeah. Okay. Janet. You're welcome. So I just started the lecture. I asked for your what I call it. I tender my apology. It's somehow you can see now. All this break. They want me now, but I need to squeeze this time to do this. Even though As today we are discussing formation density law. Is a part of porosity law, formation density law. It's called compensated formation density law, PHP. Now, it's a kind of radioactivity log. And in this case, it's called gamma-gamma log. Why? Because unlike gamma ray log, where the log son will record gamma ray radiation emission from the formation. In the case of formation density law, you introduce this gamma ray log artificially to the formation. And it is usually used, gamma ray is usually used because it has a high energy and deep penetration. That is the reason why gamma ray is used in this. And the whole essence is to get the formation density. Because when you introduce, the log goes into the formation, hit the matrix, and then return the back scattering, called Compton scattering, back, and is measured. And this helps us to measure the bulk density of the formation. Now, this is how. There is a short and long spacing detector to compensate for effect of mud cake. In the case of this log. So what is effectively measured in the formation is electron density, which is related to bulk density and which is in turn related to density of the matrix and that of fluid. Now, if you see the assemblage of it, the sound carry a blade. So as you lower it, it will be scraping part of the mud cake in the wall. And that is why this type of log is among the last sets. Because once they do the logging finish, like I told you in the beginning, once the drilling ends, the logging tools are brought in, and if it's a case of offshore, the cabin is already there by the rig. So after they remove all the pipes, they start lowering this. They must do it fast because they need to develop the well. So this one comes, the logging happens immediately after the drilling. Then once the hole is logged, then development will start. So in this type of log, carry a blade. The sun carry a blade and start scraping the mud cake in order to reduce the density so that it will contaminate, add to the density of the formation. You know, those mud cake, they are high density clay. Is that not correct? So hello? Are you listening?
Yes, sir.
I hope you are listening.
Yes, sir.
Yes.
Oh, good. The formation density compensated log FDC records the bulk density EB of the formation surrounding the borehole. And like the diagram I showed, I have explained, the source is in the lower end, then followed by the short spacing and the long spacing, because the one that is closer to the source will be the shortest spacing, and the one farther away up is the long spacing. And now when you introduce that gamma ray, it hits the if the short spacing does not pick it, the long spacing will pick the recording. So the diagram above illustrates the principle that of the two consists of gamma ray source and two detectors mounted on the part. The part is mounted into the borehole by the spacing loaded and carry a blade that is scratching some of the mooncake to minimize its contribution to the bulk density measurement, just like I have explained. Gamma rays are built by the formation and source and undergo multiple collisions with the electrons in the rock. They lose energy and become scattered in all directions. This is known as Compton scattering. Some of the scattered gamma rays return to the borehole and are recorded by the detector of the device. So, like I explained, once the gamma ray is artificially introduced, it hit the matrix. And count rates from the detector are combined to provide two signals for log presentation, both the short spacing and the long spacing. The count rate, which is the measurement they have taken from the backscattering, they are combined to give the log for formation density. Now, EB is one of the signal, which is bulk density, and the other is the P curve, and these serve as quality control. That is change in the rho. That is the change in density, and it is this we use to control the bulk density anyway. Large correction, more than 0.05 grams centimeter, tend to lower the reliability of the electron bulk density measurement. That is, if you have a measurement from the set of measurement that is more than 0.05 gram centimeter cube, the reliability of such a measurement at that point in time must be corrected for. Also, the intensity of backscatter radiation is proportional to electron density and the formation, and provided a measurement, a measure of the electron density in the material, which is approximately equal to the bulk density. The unit is gram per centimeter cube. So this is the principle of working of this particular law. And then each matrix has their different densities. The cause SiO2 has a density of about 2.614. That's the actual density, but the apparent density measurement from O is 2.648. The calcite now has measured accurately, unlike the SiO2 and so many other ones, like halite, sodium chloride. The actual density is 2.165, but the apparent density measure is 2.032, and so on for other substances. Then the true response of this formation density law. The dense low porosity formation are characterized by high bulk density values. Why higher porosity zones are associated with low bulk density grading. Do we understand that? Do we understand that?
Yes.
Hello?
Yes, sir.
Dense, low porosity formation are characterized by high bulk density value. Why higher porosity zones are associated with low bulk density grading. I think we have explained these things sometimes. Maybe during the time we're discussing sonic log. The formation density compensated log is therefore a porosity indicator. Generally, electron density E for atomic substance is equals to rho B into 2Z all over A. And for molecular substances, you have rho B into 2 sigma Z all over molecular weight. In most cases, the parenthesis equals to 1, so that the bulk density is distributed between the matrix and fluid densities, so that the bulk density will revert back to this Archies equation, where you have porosity is equals to rho Ma minus rho B all over rho Ma minus rho F. Any question? Any question?
Question. No question yet, sir.
Is that?
I said I did not have question yet.
Okay. Anthony,
Sir,
is there any question?
no question, sir.
Hey, you guys are cold this morning. What's the problem? I have apologized for any inconveniences. You should be. You don't know what I have that I'm in the other end here. I too I have some. But however, we have to keep going on. This is life. If you have any question, let's discuss it, because I want to go to neutron log. We still have a long way to go. Okay, there's no question. Neutron log. Neutron log also is a porosity log, just like the sonic and density log. Yes. Excuse me, please. Hold on. Kilo sir. Kilo sir. Ben, ó dà bẹ́ẹ̀. Ó ṣe. Sorry, please. Neutron log is also a porosity log. Neutron is a fundamental nuclear particle. Before I even start this one, what is a neutron? Janet. Janet. Hello.
Yes, sir.
What is a neutron? David,
Neutron.
you're welcome. Anthony,
Anthony.
Anthony. David.
Yano.
Sir.
Okay, Yanu. What's the
Hello,
neutron?
Sir.
Yeah, hello. What's the neutron?
It has to do with neutron now. Is a subatomic particle that has the same mass number as that of proton. But they didn't have electric charge. They are not electrically charged.
Yes, sir.
What's the neutron?
Hello, sir.
What's the neutron?
Neutron is a subatomic particle.
Yeah, I heard you. I've heard you, Anthony.
That has the same mass as a proton, but they are not electrically charged.
Okay, good. Thanks.
Yes,
Olabode, what is a neutron?
Neutrons are found in the nucleus of an atom. And they don't have electric charge.
Okay. Okay. You know, in a neutral atom, they say the number of protons is equal to the number of neutrons. And proton and neutron form the nucleus of an atom. Neutron carries no charge, just like you said. And but the proton carry a positive charge. Then the electron revolve around it, carries negative charge, and make the proton positive charge and the electron negative charge make the atom the element to be neutral. But if it loses one electron, it becomes charged either positively or negatively. Now, because neutron carry no charge, it has certain properties which make it useful for this particular log. And one of the properties is that it's very small. And the second is that it's neutrality, no charge. And because of this, it has an advantage for projectile. Now, if it doesn't carry charges and it's small, it can penetrate. You can project it. It will go far. Why? Because there's nothing to obstruct him. If you carry a charge, when you say a negative charge material, he will quickly attract to it and attenuate. Is that not correct? So these two properties are what
so we
makes
didn't get
it.
Network is disturbing. We didn't get what you said clearly, sir.
Oh, okay. What I've said is this: that in an atom, you have three particles: the electron, the neutron, and proton. And every atom has a nucleus. And this nucleus contains the proton and neutron. And whereas the electron revolves around the nucleus. Now, the electron is negatively charged, while the proton is positively charged. When the number of proton and neutron are equal, however, the neutron carries no charge, but its number is equal to that of proton. Now, because it carries no charge, it is useful in this logging because it has no charge and it's very small. And these two properties of being small and with no charge is what is ideal for him for that for him to be used as projectile. So it has the ability to penetrate deep because of the charge. Because if you carry a charge, once you project it, it can attract. When you see a negative, any other polarity, so it can attract to it and will not move far. That's what I've explained. Do we understand? Do we understand? Hello?
Yes. Yes, sir.
Oh, good. No. So the two properties, that is smallness and charge neutrality, makes the neutron an ideal projectile for penetrating matter. It therefore found a place in the arsenal of logging tools. Now, let's talk about the sources. How do they get those neutrons?
Okay.
One of it is from
Yes, sir.
chemical sources. And they are made up of two elements which react to emit neutron continuously. You know, the neutron
Yes,
is
sir.
already in the nucleus of an atom. So you need to
Yes, sir.
get in.
That
If
because
you want to produce it
it has no
chemically,
charge and very small, it can penetrate.
yes. Are you still with me? Can you hear me? Network.
Network is really bad. Yes, sir.
What do we?
I can hear you, sir.
Okay, you can hear me, eh? Janet, can you hear me?
I can hear you now.
What do we do for this network stuff now? I moved my position from where I used to be because my children are not going to school and they are watching television. If I have to stay there, they have the background noise of the television. And if I stop the television, they will disturb me. What else can I do? Hello?
You keep managing it like that.
Oh, thank you. See, one moment, please. Why are you crying? Where's your okay. Don't be watching it, so please don't disturb me. Sorry, please. So now that we know the property that makes neutron useful in logging tools, let's look at the sources of neutron. How do you get this neutron? If they are in the nucleus of an atom. Hello? Can you hear me?
Yes, I can hear you.
I can hear you, sir.
Okay. Neutron sources. One, chemical sources. Hello?
Hello, sir.
Hello?
Hello, sir.
Yeah. I think the thing updated itself by itself. The Telegram. So let's go back to it. Hello? Hello?
So,
Yeah. We have two sources of this neutron, the chemical sources and the force sources. So the chemical sources, they are made up of two elements which react to emit neutron continuously. The two elements are either protonium and beryllium, PuB, or AMB, americium beryllium. So these two elements emit proton once they come together. And it's this proton that penetrates into the formation. They get recorded. Then we have the pulse sources. This one incorporates an ion accelerator and a target, and are usually activated by switching on the accelerator. So there's an accelerator there will be an ion accelerator and a target. Once it is projected, then there will be a target. And this is done by switching on the accelerator on and off. So those are the two sources of the neutron. And types of neutron: one, we have fast neutron. We have epithermal neutron. We have thermal neutron. The fast neutron, these are found near chemical sources like the plutonium, beryllium, or americium beryllium. They are fast type. They contain substantially all the energy of several 4 MeV. The epithermal, these are neutrons which have lost some energy to each an intermediate energy level of a few electron volts. So they are these epithermal, they are not as fast as the fast neutron that are neutron. And this one are slowed down neutron with energy of the surrounding. They are eventually captured. You have heard about neutron capture before in your radioactivity. Is anyone listening? Hello?
Yes, sir. Yeah, with you, sir.
You have heard about neutron capture before. Once there is a neutron capture, what happens? Anthony, what happened during neutron capture?
neutron capture.
You don't remember? What happened during neutron?
Sir, neutron what?
Hello? Hello?
Hello, sir.
Hello? Janet?
Sir. Sir.
What happened? What happened during neutron capture? Can you give me an example of neutron capture?
When there is a neutron capture, electromagnetic energy is being produced, sir. Hello, sir.
No. What happened during neutron capture? These are things you have done before now. What? Now, do you know? Have you heard about isotope before?
Yes, sir.
Yes.
What's an isotope? What's an isotope?
The same one going on.
They have the same but different mass number.
So what causes the different mass number?
Because of different
Olabode?
number
Ian,
of neutrons.
Ian is in this class now. Okay.
Number of neutrons.
It's because of the difference in neutron.
Okay.
That's why they have this different
Mass number.
mass number.
Different. And
They have the
be
same
more
atomic
explicit
number,
the way you
different mass
present.
number.
I know that is an answer. Why? Why is that happen? What happened? Why?
Because there is
You
difference
don't
in
know,
the
right?
number
Because of the different number
I
of
don't want
neutrons
you
present in them.
because the number of neutrons is more than that of proton. I've just mentioned in an atom, the number of neutrons is always equal to the number of protons is always equal to the number of neutrons in an atom. You understand? It's always equal. The moment neutron is small, it becomes an isotope of that element. And an element, when an element captures a neutron, the element will inject that neutron, an indigestion, and that indigestion will lead to the element to split out that, spit it. And the process of spitting it out, he will break, which is called disintegration in radioactivity, and emit a gamma ray. It is this gamma ray that you use to measure in your log. Do you understand? Hello?
Yes, sir.
Hello?
So neutron is accomplished when a nucleus swallows a neutron, get indigestion, and spit out a gamma ray. In the case of thermal neutron. Now, principal uses of neutron logs. One of the uses is quantitatively. You all know what it means by quantitatively. Quantitative uses. Do you understand what I mean by quantitative uses of neutron log?
Yes.
Hello? Okay. What
Yes,
is
sir.
it, Janet? What is the difference between qualitative and quantitative? No one is talking. And it's bad. Is Yano not in this class? Hello, Yano. Yano David, class rep. He's online now. Have you in the verse?
Maybe his network is bad.
You the verse?
His network is not really good.
Okay, maybe he doesn't hear me, Abi. Sorry, it's okay. Quantitative, it means you need to do some Mhm. When
Quantitative
you
has
talk
to do
about
with numbers,
quantitative,
while
that means
qualitative
do
has to do with words.
mathematical.
Talking of numbers, arithmetic.
Yes.
While
While
qualitative
qualitative,
has to do with the words.
eh?
The qualitative
Do
has to
with
do
what?
with the words. Words.
What do you mean by
Network.
what? Explanation. I know. Okay. So,
Deal with words for
one of
the
the
meanings
principal
of
uses.
the research work.
Okay. One is quantitatively, the neutron log is used to measure porosity.
Okay.
Qualitatively, it is an excellent discriminator between gas and oil. You know, you have heard about that before, Abi?
Yes, sir.
In the oil industry, if you are doing well correlation, maybe we'll talk about, we've discussed well correlation in the class, right? Eh? Hello?
Hello, sir.
We partly discussed well correlation in class, right?
I'm not sure.
No.
Were you not in my
Apart-
last class?
I was there.
Okay, so I didn't mention anything about well correlation, Abi.
You
Eh?
mentioned it, but you didn't explain it fully.
We don't go deep into it.
That is well correlation. You see, once you are able to, the first thing in well correlation, like I did mention that day, if they are to have a workstation, didn't I mention that I will show you how to post all these things, how you post your web, post your log, all this kind of thing. But the principal thing you do in well correlation is identify your lithology, because what do you want to correlate is that lithology. Is that not correct?
It is.
Hello? It is.
It is, sir.
And I explain to you how you can use your gamma ray log to actually bring about this thing. I explained, you ask
Yes,
questions.
that's true.
Aha. That is it. Once you get that one right, the other one is just now. It is the lithology you correlate, not the fluid. But you identify the fluid within the lithology. Is that not correct? Madam Ilongo, Laja Kim proceed.
Ben, sir.
Yeah. Now, the neutron will only identify the gas zone, and we want to discriminate between gas and oil. The rest of it will identify whether it's a hydrocarbon or water.
Water.
In track 2. Because when you need those 3 logs, if you want to deal with hydrocarbon, your gamma ray log will identify the lithology. Is this shape? Is this sand? Once you get that one right, all you need to do is to focus on the reservoir. You understand? Which is the sand. In that sand, there are different fluids there. It could have the water or the hydrocarbon. Whether it's gas or oil, is hydrocarbon. Is that not correct? Now, your water will always be at the bottom. Then the oil, then gas on top. Now, the resistivity log will identify both water and both the water and the oil. Abi?
Yes.
Now you need to know what if the gas is there. You understand? Then you bring in your both the density and density and neutron. Once they cross, because you can't use your density alone. I think we mentioned something related to that. So when they cross, you can know, oh, this one on top, this what is the top is gas. Abi? Whether you answer, I know I have mentioned it. 3, it can be used geologically to identify gross lithology, evaporites, hydrated minerals, and volcanic rocks. 4, when combined, what is happening, Janet? Who is disturbing you there? No class.
Hello,
I
sir.
don't like this class. Like
Hello, sir. We are with you, sir.
Are you sure you're with me? You should be responding. Don't let me just talk to the air.
No, it's network that is disturbing.
Lagging.
Okay. What do you get? What do you have last?
What I heard last was when you were saying that resistivity log is going to identify water and oil. That's what I heard last.
Oh, you know, that means you have to listen to the audio after this. What I said is that you have after getting your lithology from gamma ray log, once you can discriminate between the lithology, the shale and sand. Now, you have that. If it's you want to deal with the fluid, if this is the fluid that is important to you, then you now use your resistivity to identify the nature of fluid. Is it water? Is it hydrocarbon? Your resistivity will discriminate it. We have mentioned that before. Is that not true?
It is.
It is.
Is that not?
It is, sir.
It is.
Okay. Now, then you need to know whether there's gas there. Then you need your porosity to. Your resistivity cannot identify whether it's gas or oil. So you now have to combine your density and your neutron, and they will cross and form like a balloon. Instead of them to go their apart, they will cross. Why? Because gas is less dense. So it will not show, it will show lower density. But with the help of neutron will be able to identify, because neutron will interact with the atoms of that gas, which I have mentioned about. In gas, it will show higher reading, whereas the density will show lower reading. Then they will cross. Once you see that cross, then you know this gas zone. Are you with me?
Yes, sir.
Yes.
Are you with me?
Yes, sir.
Yes, sir.
Are you with me?
Yes, sir.
Yes, sir.
Wow.
Yes, sir.
Best subsurface lithology indicator available. Full stop. Then principle of measurement of neutron log. Fast neutron lost energy in two ways. One, collision with particles having the same mass as neutron. That is elastic scattering. This is mainly with hydrogen nuclides. Elastic collision has a shift, slowing down length. Which inelastic has, while inelastic has a longer showing down length. Go back. Collision with other heavier particles, that is inelastic scattering, which does not result in significant energy loss. In hydrogen-rich mediums, slowing down length ROMS distance from point of emission of high energy to epithermal class medium, which is the shear compared to that of hydrogen, free environment. The slowing down length is used to determine the neutron source detector spacing. Now, what are we saying here is that length. Why in an elastic collision, there is a longer slowing down length.
Network is worst.